Okay, exam 3 final stuff. So we've already kind of have an exam 3 on this YouTube channel. Weird to say, but we do. So if you do want to go check that out, there that is also available to you. But I wanted to go through a bit more acid-base equilibria in this one, and as well look a bit more closely at oxidation and coordination and highlight some things. And I'm not going to go into great depths, and I try not to overlap. So I do suggest watching both videos when you're done with this one, but this one is more to sort of emphasize points. Again, the answers are literally going to be on the screen, and I'm just going to be talking through the equation and trying to give hints as we go along. So, all right. Acid-base equilibria. So the things that I want to point out is basically when we're looking at half equivalence point, that is the pKa. So many people don't realize this, and then when they're looking at some problems, they feel like they're missing information. I'm going to show that later on. But you do need to realize that the half equivalence point is the pKa, and if you have the pKa and the Ka value, you are able to find if you have the pKa, then you can find the pH, and then you can find the concentration of H, which means you can then find the equilibrium constant, and vice versa if it's giving you concentration. So that is a very important conversion to connect when you're doing these types of problems. As well, being aware that Ka is for acids and Kb is for bases, because a lot of people don't realize that once you're at equilibrium, you have gone from an acid to the conjugate base, and you are no longer solving for Ka. So if they gave you Ka, you have to solve for Kb, because you are now moving into Kb territory once you have hit equivalence point, because that's when all of the acid has dissociated, and now you have equal amounts of the conjugate base and the acid. With the conjugate acid, I should say. And then also, please be careful when using M1V1 equals M2V2. I literally, in my next thing, show you why you shouldn't just rely on this with monoprotic acids and bases. But you really should work out the problem and find the molar ratios. Otherwise, you are really going to be finding yourself later and being really upset that you missed this problem all because you assumed it was monoprotic or assumed it's a 1-to-1 ratio. And as well, I wanted to reemphasize something from that past video, and that as the Ka increases, the pH is decreasing, and because that Ka is telling you how strongly dissociating an acid is, and strong acids have large Ka values because they dissociate very quickly, so that would mean that then it would be a very low pH, because strong acids have very low pHs. And then something to kind of point out here is graphs like these, being able to identify what these are. If I'm starting at a high pH, that must mean that I started at a base, and I must be titrating against an acid, because then it goes into a low pH. So being able to read these graphs and manipulate them is also important. So this is the opposite, and then I start with an acid, it's titrating an acid against a base, because we end in a higher pH. So being able to sort of connect these thoughts throughout. Again, finding the half equivalence point meaning the pKa, half equivalence point meaning that if at equivalence you have equal amounts of two, and the only way you would have equal amounts is also having the same molar concentrations, and then working backwards to find, okay, well, if 50 mils, which I'm going to kind of allude to in a minute, is at equivalence point, then 25 mils would be half equivalence point. All right, so with all that being said, I kind of hinted at this a minute ago. But this is literally the constant boiling pressure, or boiling of nitric acid, and it's usually used for acid-base titrations, but it's a monoprotic acid, and a lot of people kind of mix this up because it's not your go-to monoprotic acid, as it's not HCl. And we're going to have 50 mils of this, and we're going to titrate that against magnesium dihydroxyls. And this kind of base is very easy to maneuver because you have two hydroxyl groups. What that means is when I write this balanced equation, you'll note that I'm going to have a 2-to-1 ratio of the acid to the base. And so when I have a 2-to-1 ratio of an acid to a base, you need to be careful when you're calculating through. Now in this one, I do a different kind of calculation just because I don't like to convert between liters and milliliters, but you can do that very much. I just want to note that if you are working in milliliters, then this is millimolar and not just molar. And that's how you can interchange between them. So what I did is I got the millimoles of my acid. So I took the volume times the millimole to get the number of moles in 1 mil. And then I wanted to use stoichiometrics to then find the millimoles of the base, which again is multiplying the found millimoles by 1/2. And the reason why it's 1/2 again is because of this molar ratio. And again, it's not 1-to-1, and it's very easy to then have made that mistake. So be sure you realize that some of these are not going to be 1-to-1 mole ratios, and you shouldn't rely on that. You should go through and find the balanced chemical equation. So if you're not comfortable making balanced chemical equations, please come see me in an office hour. And finally, I'm going to divide the moles of the base that I found by the volume that I found here to get the overall molarity. So again, I have this many millimoles that I calculated after my conversion, divided it by the milliliters at the endpoint, aka our equivalence point that can be seen in a titration, and I'm going to find my molarity. So this is how we would go forward finding something with something that is not necessarily a 1-to-1 mole ratio, and why that M1V1 calculation is not a safe thing to use. Okay, so this one's that kind of one that was on the homework a lot, and I like it because it's doing this 3 times over, so making an ice table, going through the ice table, etc. So that's why I put this problem in here and recommend that all of you do it. And especially because it really plays onto the 5% rule and having you question, like, okay, when I'm working through this, is this 5%? Can I ignore the X in the denominator? So first I'm going to read through and it says, okay, I'm given this concentration of HCl and this concentration of NaOH. I can already say right off the bat, because they're the same molarity, this means that when I have 50 mils of HCl and 50 mils of NaOH, I will be at equivalence point. So that's going to hit to this one. I can also say that to get half equivalence point is when I have half the amount of base, aka 25 mils. So these are things to kind of note when they have the same molarity, and that is why I can make that conclusion. All right, but first, it's saying what's the pH before the addition of any NaOH? So what's the initial pH? And that's going to be when we assume that we have not dissociated at all, right? Because we haven't added any base to, well, I shouldn't say dissociate, but we haven't added any base to take up or change the concentrations of H plus or Cl minus. So what I'm going to do is put in my initial concentration. This is about 0, and we say that because obviously there is a pH, and so you're thinking, well, there should be H plus in there, but we're assuming that this hasn't dissociated yet. There's no catalyst to do that. And again, because we have a concentration of HClO, that means that we're going to take away at the change because there's something already there, so there's going to be a shift this way if we were thinking about equilibrium, and therefore it's plus X for H plus and plus X for ClO minus. Finally, for equilibrium, that means we just add everything down. So I have 2 x's on the top in the denominator, x squared, and then I'm going to have 0.250 subtracted x. But I know that 0.250 is way greater than this ionization constant, or what we think of as the dissociation constant for HCl. And when I think of that, that makes me think, okay, well, if that's way greater, it's definitely going to be more than 5% out of range, and therefore I can ignore the x in the bottom line, and I can just say that x squared will basically be divided by 0.25 to give me similar dissociation constant. And so I use the dissociation constant here. Oh, weird. Why does it say? It should say 4 to the negative 8. 4 to the negative 8. I don't know why I have that typo, but 4 to the negative 8 equals x squared divided by 0.250, and then that means that x is going to equal the concentration of H plus, because remember, this is 1x only, there's no 2x squared nonsense, so we can just go through, remember to take the square root or raise it to the power of 1/2 to give you the concentration of H, and then to find the concentration of H, to find the pH, we use the concentration of H by taking the negative log of the concentration of H, and that'll give us a pH of 4. Awesome. Now, it's saying what is the pH after adding 25 mils? And again, when you have equal concentrations of the monoprotic titrant and the analyte, this means that this is going to be equivalence, which would be part C. But here, because we have half of that, that means we're at half equivalence. So then we can know that the pH is going to equal the pKa. Well, we know the Ka. The Ka is 4 times 10 to the minus 8. And 4 times 10 to the minus 8, if we take the negative log of Ka, then we're going to be given pKa. And that is then going to equal the pH, which is then 7.40. Awesome. And now moving forward, we're going to do what happens at equivalence. And I think this is what's mostly going to come up on the exam, and the reason why I bring this up. So that's because you're going from all of the acid to a conjugate base, and so that means you're going to need to solve for Kb. But first things first, I need to determine the concentration of the conjugate base at this equilibrium. And so I'm going to take the volume multiplied by the molarity to get my millimoles, and then I'm going to divide that by the total volume to give me my molarity. And then I need to find Kb, and Kb is simply Kw divided by Ka. And we know the Ka value, even though sadly it's butchered up here, but we know the Ka value. And I'm basically going to take Kw divided by Ka will give me Kb. Perfect. Now I have everything to make up my ice table and solve for X. And so again, remembering that my conjugate base is going to be OH minus, right? we look back at our problem up above here, and I see that HClO, that conjugate base is ClO minus, but now we're working with past equivalence point, and that means that my acid, the conjugate base is OH minus, and so that's what I want to find. And so when I go back through, I know that Kb is going to be HCl, the acid, multiplied by my conjugate base, multiplied by my base, divided by the conjugate base of HCl at this time. And that is because that is a forward reaction. Again, we're finding Kb. Always remember with Kb, you have OH minus in the numerator multiplied by your conjugate acid and or acid. So that's important to note because a lot of people do put H plus in there by mistake. So knowing, again, the difference between Ka being an acid and therefore H plus being in the numerator, and then versus Kb where OH minus will be in the numerator. All right, so I put my molarity in here. I know I have 0 of each of these, so that's going to mean this is negative x because there's going to be a shift this way in equilibrium, plus x for these two. Add them down, create Kb's the equilibrium constant equation, and then that's going to be x squared divided by 0.125 minus x. Again, 0.125 is much greater than 2.5 times 10 to the minus 7, and therefore I can ignore the x in the denominator. I then know that x equals OH minus, which is going to equal basically I know that I need to get x by itself, so I'm going to multiply 0.125 by Kb, 2.5 times 10 to the minus 7, and take the square root of that. And that's going to give me my new molarity for x, which is then, of course, the equivalent to OH minus. Then I know that when I have the concentration of OH minus, I can then use POH, because remember, our big goal is to find the pH value. And if I want pH, and I'm using Kb, then that means I have to use my POH plus pH equals 14 rule eventually. So I know that POH equals the negative log of the concentration of my hydroxyl, OH minus. So I take the negative log of my concentration of OH minus, and that gives me 3.75. Again, this is POH. This is where this will be an answer. It will be an option. Don't be fooled. This is POH. If it's asking for pH, you are looking for pH. Please don't make this mistake. I did it, and that's why I'm so, I think, naggy about it, is because I remember getting back my exam, and luckily our exams are not multiple choice, so I was given more marks. You guys are not given that option, which is why I think I'm so worried about it. But yes, please know that you're finding POH. So pH will be 14 minus POH, which will give me my pH value. Again, another way to know if you are like, wow, that's a really low value, is remember that you're adding 50 mils of a base. If you've added base to something, that means the pH should increase. So that's another thing to think of when you're working through these, is do a quick common sense check. If I've added a lot of base, it should have a high pH. If I have added a lot of acid, it should be a low pH. That thing that I was talking about earlier, just this common sense checks really, really help. Okay, quick break, deep breath. Here we go. I'm moving on, not for mean reasons, but because I assume you've paused the video and you are back. For oxidation states and coordination numbers, the most thing to consider is salts. One thing that people, I think, make a big mistake on with salts is that they then use the salt anions to then make the coordination number. If it's great, I think, and the problem is, where this goes really sour, is if you have a tetrahedral, and then that tetrahedral, you're thinking, oh, but if I add 2 more, then I'm an octahedral, and I've seen that kind of thing before. I think it's easier to see with octahedrals because then you get 8 coordination number, and you're like, well, I've never seen that before in my life. It must be octahedral. That's kind of how people deduce that, but beware that if something is in brackets, I am looking for the coordination of what's inside the brackets and the metal specifically, and not only just metal, but the transition metal in that complex. And also knowing your coordination numbers. So again, something like this means that B is actually going to be coordination of 1, 2, 3, 4, and 5. Or no, wait, 1, 2, 3, 4, 5, 6. So this is octahedral, but this one is pentapyramidal, I think. Yeah. Things like this, being aware of how many things are attached. This boron here has 1, 2, 3, 4, 5, 6 things attached. This one here has 5 things attached. This carbon has 4 things attached. This tin has 4 things attached. You know, paying attention to these kinds of things. This chromium has 6 things attached. So this is an octahedral complex attached to a tetrahedral tin. Making sure we kind of understand that these coordinations have different things, and being able to identify them is very important. And then please be careful with math with oxidation states. I think the only time that I had people come to me with a big question mark is when they had a simple math thing and then they like went, oh, I should have seen that. Just double check, make sure you carry everything over. If you have to take the step all the way down to the very like x equals this, not just like, x plus 3 equals -1. You don't want to then say x plus 3 equals -1 and therefore x equals 2 when it's really -4, I had to think about the wrong answer for a minute, sorry. But yeah, just be aware of simple math. Okay, so I'm just going to do all of these. In the exam, you will be asked to either find the oxidation state or the geometry, but I want to go through both of them and kind of hit two birds with one stone. So this is not exactly how the exam is, how do I want to say this? Phrased. Instead, it usually says determine the geometry of the metal species or determine the oxidation state, but I've just kind of smudged them together. So the first thing you're going to look for is which ligands are neutral and which are charged, because that's going to tell you what can I move forward with. So when I look at this up here, I'm like, okay, well, I know that CO is not charged. Carbonyl is not charged. It's the way that the carbon is a double bond to the oxygen, and therefore it's not charged. Meanwhile, this CN group is triple bound, but it has a negative charge on it. So if you have trouble memorizing these, maybe write a series out to the side with their charge on them so you know what the charge is. This one's particular in that it is not a salt. It just gives you an overall charge on the complex, and sometimes people forget this charge, which is I think why it was most missed. One of the most missed is because they forgot the charge on the outside of this complex. So be sure that if the whole complex is charged, then that means overall the charge on iron plus the charge of these 4 cyanide groups plus the 2 carbonyl groups needs to equal -2. So I know that I have to add all these together. So my CN has a -1 charge on it, so -1 times 4. My carbonyl groups have a charge of 0, but there's 2 of them. And the overall charge in the complex is -2. So -2 equals 0 multiplied by 2 plus -4 will plus unknown. I gave the answer in my head. But basically then that means that I have 0, so if I subtract 0, I still get -2. And then if I have -4, I'm going to add 4 onto the other side, and therefore the oxidation state of iron will be +2. The other thing I have to do is find the geometry. And what's nice about this one is whenever you have 4 plus 2, you're already going to know that this is octahedral. And that also makes sense because this is not a salt, so we don't have to worry about any spectator ions getting in our way. Okay, this one is actually a salt, and now we've got something to worry about. And a lot of people mix this up, especially because they say Cl2, and Cl2 does not have a charge, it's 0. But on a salt, when we see it in a complex, that means that you have 2 Cl- ions, because these 2 Cl- are within the brackets, and that means the Cl is actually attached to the cobalt center. So this means I have, NH3 up here, and I'm not going to really draw out the NH3, but I have like 4 NH3 sitting here, and then I have 2 Cl groups that are also bound to the center. So you want to be really aware of what the terminology or what the meaning of that is within the brackets, and that is what this means. And then I see that it's a salt, and I know that Cl has a -1 charge. Again, we kind of hinted at it here, but that means that if this is -1, then the whole entire complex here then must be +1. So that's what we kind of needed that Cl to note, is that this whole complex actually equals +1. I know that ammonium ligands are a charge of 0, and again the Cl is a charge of -1. So I go through and I have 0 times 4 equals -1 times 2, and then if I take the charge of cobalt, which we'll put as x, will be +0 plus -2 equals +1. Then I know that I'm going to add 2 onto the other side, and then that's going to mean that cobalt is going to have a charge overall of +3. And then this one again, I know that this Cl is actually a spectator and that it is part of the salt. And in reality, what I want is these 2 ligands here plus the 4 ligands here. And that equals 6 ligands, which will be an octahedral complex. Okay, so determining the oxidation state and geometry of the metal species. In this one, there's 2 trick things that I wanted to show you that a lot of people ask me. And one is, the first thing being, I should get my pen ready actually, is that there's a 4 here. And when there's 4, then we're like, okay, well, is it tetrahedral or is it square planar, Victoria? And so the way that we know that this one is square planar, so kind of jumping ahead here, is that I have 4 bromides, and those bromides are all going to be pulling in the same direction. Or not same direction, sorry, but the same electronegativity, and therefore they're all going to be spanned out in the same plane. So that's how I know that FeBr4 is going to be square planar. Okay, the other thing I need to know. So I have a salt, and because I have a salt, I need to know what the charge of the complex is. And this one is slightly different from before because I know that barium here is an earth metal, and that is going to have a 2+ charge on it. And so that means that I'm going to need 2 of these, but they're going to have to be negative. So remember, there's 2 of them here, which means the actual complex is not 2-, but 1-. And that's because I have 2 of them. So the actual complex is -1. So this is something to be careful of because a lot of people will say, oh, barium +2. Okay, the complex must be -2. It's not. It's -1, and there's 2 of them that are coordinating to this barium. Okay, so the bromide we know is -1. So for the bromide ligands, I have -1 times 4. And I know the overall complex equals -1. And therefore, I know that -4 plus X will equal -1. If I add 4 onto the other side, then I know iron has an oxidation state of +3. All right. Our favorite thing, ligands and splitting diagrams. Love these. They're our favorite thing in the world. They're super duper confusing. We hate to love them. Someone asked me a very good question in why in octahedral complexes the z squared and the x squared minus y squared is higher in energy. And then that's basically flipped for tetrahedral. And so I just wanted to quickly show that it's because the way that in an octahedral, the way that I don't know if you've seen an octahedral, but the octahedral complexes do have 2 groups that sit on the axes. And if you notice, then their other groups then sit on the axes. And therefore, all of these 2 orbitals are specifically orbitals that sit on the axes. And therefore, if the orbitals are interacting with the ligands, then you have a lot of high density energy. And so usually the electrons like to hang out in between the axes if they can. They don't always get to, and they're of course forced into the dz squared and dx squared minus y squared. And that's why those are higher energy. And that's, of course, we see that because we place the electrons up there, we know. But that's why they're so much higher in energy, because we can see that they're on the axes, and therefore they're on where the ligands are, and they're in each other's way. Opposite to tetrahedral, tetrahedral likes to have its 4 sitting in between the axes, and therefore these are going to be higher in energy. But they're not so much higher in energy because, again, there's only 4 ligands, so it's not too much of a competition. The other thing I wanted to note, so weak field ligands are too weak to push all the electrons together into the lower set. Same thing is that strong ligands are strong enough to then lift the electrons into the higher set. That's how I remember the difference between the 2 of them. High spin, though, means that they're going to be able to occupy high spin states, aka the higher level. Low spin complexes are then going to be the only ones that can occupy low spin states, and therefore are on the lower level. Those are the 2 ways that I try to remember those 2 terminologies when you're working through these. And then to know that tetrahedral complexes cannot be low spin. Cannot be low spin, cannot be weak, or cannot be cannot be strong field. And that's because, again, like I said, there's a few exceptions, but it's mostly because those 4 ligands do not interact the same way as the 6 ligands do. But I'm not going into all of that. It's too much information overload. All right, so we're going to look at this complex here. Pull out my pen. The one thing that I know is that perchlorate has a -1 charge on it, and therefore that means that this overall complex over here has a +1 charge on it. So this is going to help me when I'm determining the complex over here. Has a +2 charge on it. And that's because I have 2 of them. So this is going to be +2. And then I know that water is neutral, and therefore the Cu will be 2+. So then when I look at a periodic table, I look at Cu2+, and that means that I get my 2 electrons away from the outermost shell, 4s. So then I have 3d9 electrons to work with. I also know that water is a relatively, we feel it's a weaker field ligand. It's literally smack dab in the middle, but we consider it weak field. And therefore when I'm filling these up with my 9, I'm literally going to put my 1, 2, 3, 4, 5, 6, 7, 8, 9. Wonderful. Easy peasy. The one thing to note with these is that you are pushing up. Now this one, because it's 9, you could have technically filled it up either way, but I wanted to point this one out simply because, again, you're working with a salt, and sometimes it is hard to see the charge on perchlorate. And again, even I made a little mistake there as well and almost made an error. So just be aware when you're working with salts what the charges really are. Again, this one is another doozy. So much fun. I do know that sulfates have a charge of -2, and that means that overall this is -4. I know ammonium has a charge of +1, and there are 2 of these. So if I have +2 and -4, then this complex right here must be +2. Again, water itself, again, some people mistake this for OH, and then again, luckily it's weak as well, but just be aware that it is water. And also because if it is OH, then that would mean that this is contributing -6, and then our charge on nickel will be wrong. So be sure we note that this 2 here does mean that it's water. And this means that the +2 charge on this complex is directly to nickel, so nickel is really 2+. And then I know that I take those 2 from the outermost shell, and then I'm left with 3d8. And then I go through and I'm like, okay, again, it's a weak field ligand, and so all I'm going to do is go 1, 2, 3, 4, 5, 6, 7, 8. Perfect. Okay, this one. I'm working with iron, and I have water and CN. Now I've got a bit of a mix. And that means you're going to overall wonder, well, what does that mean? But in reality, we've realized that, again, when I'm working with this kind of thing, I'm going to use my pen, in that, okay, overall, this is going to have a +2 charge on it because, again, water is neutral and CN is -1, and I have 2 of them, and that means that from this 4s, I take away from this outermost electron, and I'm going to have 3d6 be my overall orientation, so I have 6 electrons to work with. And I know that it can't be low spin. So luckily, even though these are competing on the scale, and this is strong and this is relatively weak, I know that it can't be low spin and it's going to be high spin. And therefore, it's going to follow the rules of a weak field ligand. But someone asked me, like, okay, but what if I do have a tetrahedral complex, or sorry, not tetrahedral, but an octahedral complex? Then I would tell you that whoever has the stronger field ligand is the one that you should work with. So if this were, say, octahedral, and I had 3 waters and 3 cyano ligands, it would be overall actually low spin and strong field because CN is much stronger. Because if we look here, CN is the strongest ligand that we get, and H2O is kind of in between. All right. So then I know that it can't be low spin, though, because, again, it's tetrahedral, and therefore I can cross this whole shebang out. And I know that it's going to be high spin regardless of what the ligands are. And then that means that it's going to have 4 unpaired electrons because it would be 1, 2, 3, 4, 5, and 6. And I'm going to have 4 unpaired electrons. Therefore, I can tell you that it has a very high magnetic moment. 4.9 is a very high magnetic moment. Wonderful. Okay. Now I'm looking at manganese, and manganese trioxygen. And I know that oxygen has -2 on it. -2 times 3 is going to be -6. And then I know that there is 2 manganese, so -6 divided by 2 is -3. And I know that to balance out that -3, then manganese must be +3. Perfect, because +3 times 2 would equal -6. Perfect. I know that manganese has 4s2, 3d5, and therefore I'm going to take from the outermost first, and therefore get rid of my 2 electrons in my 4s shell, and then I'm going to get 1 out of my 3d5, and that leaves me with 4. Great. Ooh, I've made a mess of this. But am I high spin or am I low spin? And I can tell that just by the ligand, and that oxygen, or bloop, bloop. Here, when I look at this, oxygens are always a bit weaker. And therefore, it means that it's going to be high spin. It's going to have 4 unpaired electrons. So it's going to be here. And again, that means that they're all unpaired. So it means that it's not going to be this one. All right, the other thing I wanted to note, because I'm at the end of my show, especially with these kinds of things, is that remember that the more things are paired together, the less magnetic it is, and the more things are paired together, the less colored it is. And that's, I think, all I wanted to cover for this, for exam 3. Again, please go check that final video that was exam 3 that goes through a bit more details about what was going on, and then as well go through and find things that maybe you're not too confident about. A lot of people had trouble with the complexes and things, so come see me about that if that's what's bothering you, or colored things, because that's kind of what a lot of people wanted help with. And then let's see, tomorrow I'm going to post your video for entropy, so that will be your help for the entropy exam, or the entropy part of the exam. All right.